to 10 a.m. slot, spread over 4 rooms. So your room number I will announce through email. I will also try to send you the syllabus. So overall, so starting today, you may see a gradual transformation in the tone and tenor of this course. Essentially, we will go from global analysis, system level analysis, device level analysis to local analysis. So the approach details will be somewhat different, even though the subject is the same, fluid mechanics. Subject exploits the natural laws. So your first exam will be essentially about global control volume analysis. This is the outline of the syllabus. I'll send you just for confirmation on email. Let me also announce that there is nothing like makeup for the mid-semester exam. There is no pro rata calculation. So that means you please manage your health and be in good shape. Okay. Some confusion. Some students came to me and said, is this P, is this rho? I thought you were familiar with, let's say, English language or symbols and also Greek symbols. So I will send you a small handout on Greek symbols. But the common ones you should be familiar with. What is this symbol? I think it should be clear, it's a mu. And in our context, it is, I think some tables it is mentioned absolute viscosity, dynamic viscosity. Sometimes simply viscosity. What is this symbol? Rho. That we use for density. The ratio of the two is called kinematic viscosity, because you have taken out rho, that means the mass dimension out. This is nu, 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 mu, mu, rho, rho. So, they have their own units. This is sigma, and we have called it the stress tensor in units of pascals, which is Newton per meter square. This epsilon represents strain, but the fluid response to an applied stress is flow, which is strain rate. So, it is epsilon dot, you can see a dot above. What are the units of strain? It is a change in length per unit length. So, no units, and if you put a dot, it becomes second inverse. So, these are symbols we will use a little more often than in the past. So, in the previous discussions, we always said, let us say u is x component of velocity, but as we go to a local description of flow field, we will encounter a velocity vector whose components are u, v, w. Now, it is algebraically quite involved, dealing with 3 components u, v and w. So, we may go up to 2 components u and v, just for simplicity. What is this? P, which is pressure in our discussion. So, u meters per second What is the difference between sigma and P? P is a part of sigma. What is the other part of sigma? Shear stress, right? And shear stress we have used tau. For wall shear stress, tau wall, we put a symbol, a suffix W, that is the shear stress at the wall. You are always worried about the force acting on the object because of fluid motion. So, pressure is P anywhere, but we are also interested in pressure at the wall. Similarly, shear stress at the wall. So, when they act on the wall, they have their own directions. Pressure is normal to the surface, shear stress is tangential to the surface. And we combine all the information and construct the force acting on the object. So, certain amount of fluency with symbols is essential. Reverting to dimensional analysis or principles of similarity, sometimes it is called non-dimensionalization. Why did we get into that topic? Because we were using handbook data to close our system of equations. Close meaning converting inequality. Second law of thermodynamics brought in inequality. We wanted to replace it by equality. For that, we needed a tabulation of forces and losses. And then we found the handbook information to be in dimensionless form. So, for flow through a tube, we wrote the functionality to be delta P, pressure drop, which is a measure of losses taking place in the tube. Rho mu u d L epsilon equal to 0 as the functional relationship. Through a process of non-dimensionalization, we brought it down to on the left hand side is friction factor given a symbol F. So, it is this data which is given to you in the handbook. Now, you will notice an important result. Of course, there is that previous result that the laws of similarity confirm or guarantee that this data that you have generated in a model experiment can be used in a prototype, because principles of geometric similarity and dynamic similarity are both fulfilled. That is to say, if L over, in this case, epsilon over d model equal to prototype, RE for model equal to prototype, then friction factor for the model will also be equal to prototype. Then with that value of F, you continue carrying out prototype analysis. So, we looked at many examples, water being pumped out of a well or a reservoir driving a turbine. So, many such examples were looked at. Now, one more advantage of this representation is compactness. So, if you had to represent the governing equation in dimensional form, then you would have to specify delta P for every rho, every mu, every u, every d, every L and every epsilon. But now, in reduced form, you just have to give friction factor with respect to Re and epsilon over d. So, you have compacted, or you may call it compressed. This is a compact representation of physical data. One other example shown to you was force acting on a circular cylinder, specifically drag. Drag is that component. Force is a vector, so you have to specify the direction. Drag is the force acting on the object in the flow direction. What is this flow direction? It is the upstream flow direction, because close to the object it is going everywhere. So, when you have a reference direction to be specified, it is the upstream value. Upstream is ahead of the object. So, this relationship was written as drag rho mu u dl, there is epsilon also, but let us say for the time being we assume the surface of the cylinder to be smooth. So, epsilon is 0. So, this we were able to reduce to a single parameter, the left hand side being given a symbol C suffix capital D called coefficient of drag or drag coefficient. And it is only a function of Reynolds number. Now, this quantity d times L is the projected area. So, this is sort of important from an applications viewpoint. For flow through a tube, we said you may replace a diameter by hydraulic diameter if the tube cross section is not circular, or you have a free surface formed inside the tube, it is partly filled, or it is an elliptical cross section. So, it turns out that within the extent of uncertainty in the measurement data, you can use that relationship derived for a perfectly circular cross section can be extended to non-circular cross sections by replacing d by hydraulic diameter. Something similar happens for this external flow problem. If you replace dl, which is the real projected area for a long circular cylinder, by the projected area of any other object, that relationship remains practically unchanged. So, it is a useful information to have. That means that handbook data does not hold only for real circular cylinders, but a whole family of objects that look like a circular cylinder, for example, square cross section, let us say, can also be analyzed with this functionality by replacing the quantity d times L by the projected area. Anyway, we have not looked at examples of that type, but it is there in the book. It says there is a tube containing oil and it is partly filled, and you have to find, given the inclination, find the flow rate. There you can find the friction factor by working with hydraulic diameter. So, as an application of the drag coefficient formula. So, you remember it has this peculiar shape. Why this shape cannot be answered in the context of global analysis, which is why we will be pursuing local, that means a detailed approach to flow distribution. So, just an example was particle motion in a fluid medium, also called particle trajectory. A simple one-dimensional example. Let us say you have a liquid column in which you introduce a particle. Now, it does not matter whether it is cylindrical or spherical or any particle, because the CD versus RE data can be used, and it starts to move under its own weight. So, let us say this is the z direction, this is the direction of gravity, and let us use the symbol u. So, we can write an equation of motion So, let me just for definiteness, let me call it u p, because we have used u for the fluid. So, u p is the particle velocity. This mass time, we are doing an analysis of the particle now. So, this will be equal to the forces acting on it minus rho, the second term. So, this is rho f g times volume, which is buoyancy, and then it will also be resisted by the fluid force acting on it. Okay. So, the data was generated for a fixed object, flow going past the object. Now, we are using it in a situation where the fluid medium is fixed and the particle is moving through it. So, that will be minus C d half rho u p square times projected area, subject to some initial condition. So, this is a differential equation, where C d is a function of R e, and R e is rho u p diameter over mu. So, you can see that u p appears as u p square, it appears through C d, and then you have to integrate this differential equation. Once you have particle velocity, you can integrate particle velocity and get particle position. If you integrate velocity, what will you get? Position, right? So, you can trace its movement in time. Of course, you can look at the limiting case. See, initially what is the velocity? It is 0. So, what do you expect the solution to be? Initially it is 0 and it will accelerate because of its own weight, but with the passage of time the resistance offered by the surrounding medium also keeps increasing. So, the force acting on the object keeps decreasing. At some point it will become 0, the particle will move with constant speed. Sometimes it is called a terminal velocity. Okay, this is called terminal velocity. So, how do you find the terminal velocity? Set left hand side equal to 0, assume u p, find C d, and then solve the right hand side, the algebraic equation on the right hand side for u p. Then find Reynolds number again, update your drag coefficient and repeat, or follow that bracketing approach we had discussed. That means, define the right hand side as some function of u p, guess u p so that the residual is positive, guess u p again so it is negative, and then you have bracketed the solution. Suppose the fluid is also in motion. Let us say you have a prescribed flow, then the fluid dynamic force will be replaced by CD half rho. See, in buoyancy it is fluid density. In the definition of CD also it is fluid density. So, you can, but the particle will have its own density that will determine its mass. So, this will be u minus u p square, and then you will have to assign a symbol either positive or negative. So, if the fluid is very slowly moving, particle is rapidly moving, then the force acting on the particle will be opposed to fluid movement. But if fluid velocity is higher than particle velocity, it will try to push the particle. So, that sign will come. Symbolically, we write it as u minus u p divided by the modulus of u minus u p. Okay. So, if u is 0, it will automatically produce a negative sign. So, this will generate a sign for the fluid dynamic term. So, this is it's either positive or negative. It will generate a symbol or a sign for the rest of it, and the CD will be based on Reynolds number, which is rho times u minus u p d over mu. It is based on the relative velocity between the two. Now, if you have to integrate that differential equation, it's somewhat difficult. So, in most situations, we have been seeing approximations all the time. How do you approximately solve the differential equation? You can replace the derivative by a quotient. Okay, so, we replaced an integral by a sum in previous discussions. We did not solve the integral equation. Now, we have a differential equation which looks somewhat complicated. By the way, it can become even more complicated if the flow field were to be two-dimensional. So, then you will have two components. You will have to write two momentum equations. The particle will have two components of velocity, which you can define in the x and y directions. Flow field also has two components, u and v. So, you will have two momentum equations. This drag coefficient will be in the direction of the relative velocity between u and u p. So, these complications have to be factored in a multidimensional flow field. But how do you integrate? One possibility is to replace the derivative. So, now where n is the time instant, with you can write u p at n equal to 1 equal to 0 and t n equal to 1 equal to 0. Okay. So, n equal to 1, now you have created an index n. N equal to 1 is the initial time instant when the velocity is 0. Then replace the derivative by u p, and the change in velocity divided by change in the time instant. To do this, what is the requirement? Requirement is that the time interval you consider be short, be small. So, T n plus 1 minus T n, which you may call delta t, is a small quantity. So, suppose the particle evolves over a time frame of, let us say, 1 hour, then something like 1 minute is a small time interval. If the whole thing happens in 1 minute, then 1 second would be an appropriate time step. Suppose you have a particle moving in air, which is a fluid. It will move and reach, let us say, terminal velocity in a matter of 5 seconds. Then you have to use a millisecond as your time interval. Suppose it is moving in water, it may take 3 minutes, let us say. So, then okay, so let me go back. The data was generated in an experiment where the object was fixed and the flow was taking place. Now, we are using it in a situation where fluid overall is fixed and the particle is moving. So, it is just a change in the frame of reference. Now, the third instance is where fluid is moving, particle is also moving, then it is the relative velocity between the two. Okay, so, now if you have to use this, now becomes an algorithm, because then you have to tabulate. Start with n equal to 1, T n is equal to 0, u p equal to 0, evaluate the right hand side at that time instant, and then find from this equation what will you find? U p n plus 1, which is the next time level, and then repeat it for all values of n till u p becomes nearly constant, and then you stop. So, this becomes the basis of your algorithm. Okay, so, and the expected solution is just shown here. So, it is an example of carrying out particle trajectory problems. So, I think in your high school you learn projectile motion and you neglect this term, the last term. So, in more realistic settings, it is the last term that governs the behavior of the object in flight. So, now we move on to asking somewhat more difficult questions. But the motivation for asking the question should be clear. What is the motivation? We looked at handbook data, we looked at friction factor data, and we saw there was a jump. We saw that surface roughness was important at high Reynolds numbers, but not low Reynolds numbers. You saw that the slope of the friction factor relationship also changed with Reynolds number. In case of drag coefficient, it decreased, then constant, then sudden dip. So, it is quite natural to probe a little deeper into the subject and ask, why do we have these details? So, those can come only when you look at the details of the flow field. So, that is the motivation behind asking this question of local versus global description. Now, play some videos. Hopefully, these videos work. So, let us start with flow through a tube. I am going to play this video. This is flow through a tube where the fluid speed is on the lower side. So, if you think of the friction factor Reynolds number drawing, Reynolds number is on the lower side. So, you have friction factor decreasing with Reynolds number, but there is no effect of roughness. Oh, it is running over and over again. Okay, how do you, let me stop it. So, how was the experiment done? There is flow from left to right and you inject a dye on the left hand side. What is the color of that dye? Blue, green. This is green or blue? That question cannot be so controversial. I don't know. What is the color? We'll take it as your opinion. Black. So, so that's why they said that was like a local opinion versus global opinion. Never go by the local opinion. But that's what we are going to do, and we are going to trust it. So, this greenish looking, at least to me it is greenish looking, is introduced at the center. Can you see this arrow? It is introduced at the center. So, and then you can see that it is just moving straight through the tube. So, you have to see, if you look at a video, you can't really draw any conclusion unless you have a comparison video. This is at a lower speed, so you can immediately ask, what about higher speed? So, then you can compare low versus high. So, it's okay. Now, let me stop this and run a similar experiment at a higher flow rate through the tube. The same tube. So, they say when the scene is disturbed, you recognize it faster. When everything looks smooth and normal, you don't appreciate it. So, but you do see a disturbed state of flow, yes or no? Okay. Along the core of the tube. The only difference is the flow rate. That people, there was a question, what do you mean by flow? That's what people keep asking. So, flow could mean velocity or volumetric flow rate, and if you multiply by density, it is mass flow rate. Okay. So, when I say flow, I mean both velocity as well as volume flow rate. The volume flow rate is higher, and the dye, what is dye? It is like ink, and it is added, you are able to see that color because that liquid is water. Okay. It is a water compatible dye, let us say. You can't have a liquid dye in air, it will just settle down. It is water, and the flow rate is increased, and you can see that the flow is highly disturbed. Okay. So, this is the difference between low speed, high speed, that means low Reynolds number, high Reynolds number. But there is no way of bringing in this level of difference in our global analysis. You can't do anything with it except through handbook data. Otherwise, the mass, momentum, energy equations are applicable whether it is low speed or high speed. So, that in a way moves us towards carrying out dedicated local scale analysis. Now, let us look at a video where we have slow flow past I think it is a cylinder. yeah, it's a cylinder, slow flow past a cylinder. And then we look at rapidly moving flow past a cylinder. Okay, so once again, you can see these the die going around the cylinder. So you can look at this arrow of my pen, and you will see that flow is going around smoothly. Okay, so now it will repeat. So let me stop it. It shows a cylinder moving relative to a stationary medium. Why? Because it's very difficult to move a liquid at very low speeds. Okay, it's easier to move the cylinder at low speeds in the lab setting, because if you have a pump or something, then it will have a finite velocity. You want to make it very small. You want to look at Reynolds number of, let's say, 0.01. Okay, the velocity may be just too small, so you move the cylinder. Okay, so and then you look at the flow lines. Okay, so equivalently, if flow had taken place past the cylinder, the flow would have happened along the green lines. Okay, and then you see that it is going around, these green lines are just going around the cylinder. They conform to the shape of the object. Cylinder going around smoothly. So this is like the laminar flow counterpart for flow through a tube. Flow, you introduced flow along the axis, and the die remained along the axis. You increase the speed, and it tends to oscillate and mix with the surrounding fluid. You can see it here that the flow is going around the cylinder. Okay. This is what happens at low speed, for which you had that CD versus RE curve, you had that diminishing branch. Now, let us see what happens when the speed is increased. Speed is increased, but the video has been slowed down. Okay. So, this is here the fluid is moving, cylinder is fixed. You see that the fluid is not staying attached to the surface of the cylinder. This is also repeating. So, look at the arrow. This, you can see the arrow. You can see that flow remains attached to the cylinder, but at some point it leaves the surface of the cylinder. It is not going along the contour of the cylinder. Okay. Now, if I increase the speed further, you will see that more or less this pattern is reproduced, which is why that CD versus RE curve tends to become flat and nothing happens. Now, what will happen at very high Reynolds number? We saw a sudden dip in the drag coefficient. That point we discuss later. But right now, I just wanted to compare low and high speeds, and you see that the details, the local details are very different. There is no way you can bring in this information in global analysis of the flow phenomena. Okay. So, that is the motivation behind going into a local description of the flow field. Okay, so now whether it is local or global, in our approach we are in the continuum scale. we continue to be governed by the natural laws of mass, momentum, and energy. Now, this energy equation is supplemented by the second law of thermodynamics. So, you remember the we had carried out control volume analysis, and we wrote the mass balance equation. Equal to 0. So, this was at the scale of a full control volume. If you remember, we had simplified it to this form. Now, from this point onwards, we could either shrink CV to a continuum point, or we could also argue that control volume is unspecified and therefore the integrand is 0. So, quickly conclude that the time derivative of density plus del dot rho u is 0. So, this equation, what is the scale at which this equation is presented? It is a derivative with respect to time. So, it is instantaneous. That means, it is a very short time interval, and the derivatives are evaluated with respect to small neighborhoods. So, it is really at a point. So, this mass balance equation is certainly on a local scale, while the integral equation was on a global scale, because it is at the scale of the control volume. Now, you have a differential equation, which is definitely local, because when you talk of instantaneous velocity, it is velocity at this time instant, rate of change of velocity or rate of change of density at this time instant. So, we are talking about now, and the point is here. So, it is a here and now approach. It is called a local description. So, this is the mass balance equation, and if the medium is incompressible, then the first term is 0, rho is constant, comes out, and you get the mass balance equation in the form del dot u equal to 0. So, what is the coordinate system for this equation? By the way, control volume may be anything. You but when you write a differential equation, you have to specify the coordinate system. Is it Cartesian? Is it cylindrical, spherical? So when you write del dot u equal to 0, what is the coordinate system of this equation? Which one is it? Is it Cartesian or is it cylindrical, spherical, or is it coordinate free? It is coordinate free form. So to simplify it further, you have to specify the coordinate system. So let me just wind up by saying okay. So thank you, and we continue with mass and momentum equations, local versions, in the next class. The idea would be to explain